Good morning. In this video, we are going to go back to studying chemical equations and their heats of reactions, and we are going to apply a very useful law called Hess's law to do that. Let us consider this chemical reaction here, NO I already messed up. I know it looks a little bit strange, but we have a single oxygen goes to NO2, and I want to know the delta H of the reaction equals question mark. Number one, we should assume that delta H is in kilojoules per mole of reaction. Unless otherwise told. So the important part is that it is per mole of the reaction. You could always adjust it to be per blank mole of some reagent, but all of the reagents actually here are coefficient of 1, same with the product. Number 2, when we verbalize this delta H, we could say the delta enthalpy of reaction RxN abbreviation, or just as correct, delta heat of reaction. Because we assume that the reaction is done open to atmosphere, the pressure is actually constant. So do you remember this equation here? Delta H of the reaction equals the heat that is absorbed or released in that reaction divided by the mole of reaction. One cycle, one mole of cycles of the reaction. And let me put a box around this. This is an important equation. Actually, an important equation and an important concept to keep in mind. We'll be doing a lot of these where we are going to figure out the heat, but related to the delta H. This is at constant pressure. Again, most reactions you do, especially in lab, will be under constant pressure. Third, enthalpy is a state function. Enthalpy is a state. Do you remember what that means? It means that delta H is the same for every H final minus H initial, no matter what path is taken. H final minus H initial for a certain process or reaction. This is going to be very important when we discuss Hess law. Just as a reminder, for instance, if I have, let's say, a 6th floor building, and I have one person take the elevator, and that elevator goes up to the 6th floor from the 1st floor. Okay. And we have another person take the stairs. etc. Okay. Well, the gain in gravitational potential energy should be the same for both of them. Okay? So in terms of terminology, we could say that potential energy, or let's say the change in potential energy, is what's called a state function. It only relies on the initial and final state, regardless of how you got to that final state. But what is the non-state function? We could think of the distance traveled, or the maybe even the energy expended is different. But I mean, like the number of steps taken, that's called a path function. It depends on the path, the number of steps. And we're going to apply that to chemical reactions using what's called Hess's law. Let me give you finally the definition for Hess's law. We're going to apply this concept of the state function to enthalpy using Hess's law. The change in enthalpy when reactants are converted to products is the same whether the reaction takes place in one or many steps. Okay. Okay. Very analogous to our elevator person and our stairs person. Okay, that is Hess's law. How do we apply this in a problem? We are going to go back to our equation and try to figure out the delta H of reaction for that targeted equation based on several steps. Okay, let me set up the problem one more time. What is delta H of the reaction of? To tell you the truth, I'm not going to put the states because everything that we work with for this problem will be in gas. NO plus O again goes to NO2. And here's what's given. This is our target, and what's given are 3 reactions, supposedly steps from the starting material to the product. The first reaction is NO plus O3 goes to NO2 plus O2, and its associated delta H equals negative 198.9 kilojoules per mole. Let me finish the other 2 reactions, and you can copy. This is a little bit strange, but we have 3/2 O2. Normally when you balance an equation, you want to keep it as whole integers, but I believe that this is done because the associated enthalpy was per mole of O3. So they force this to be coefficient over 1. Delta H equals negative 142.3, and same units. O2 goes to 2O, some type of dissociation. This really requires energy, so this is positive 495. That was expected that it was positive. You're breaking up oxygen-oxygen bond. Okay, a couple of tips, and then I'll show you how to solve this. Tip number 1, we need to manipulate the reaction steps. So when added, it results in the target reaction. Okay, let me organize this so it's very easy to tell which reaction I'm trying to manipulate. This is the target. Obviously, this is the value that we need, and it's going to be in kilojoules per mole. And we're going to call this reaction A, individual step reaction A, B, and C. Okay. Before we solve this problem, a couple more tips. Focus first on a compound that shows up in one step reaction. Don't try to resolve a compound that shows up in more than one step. Okay. Number 3, the very last thing. There may be a step that does not have any of the reactants or products. Why would they include that? Does not have any reactants or products. That reaction is used to cancel out any unwanted chemicals, any unwanted compounds. For instance, this equation here has an NO. We have an NO as a reactant, but equation A also has O3. O3 is not seen anywhere in the target, so O3 has to be canceled out at some point. Okay, enough setup and enough tips. Let me show you how I would solve this in a hopefully systematic way. Manipulate, here. Focus first on a compound that shows up in one step. I'm going to focus on NO because it only shows up in reaction A. So I am going to recopy A, and because it's one coefficient on the left, and already it's one coefficient on the left, I'm going to keep as is. And yes, I am going to recopy it. And I'm going to call this A prime, manipulated A, but I really didn't manipulate it. I just kept it as is. If you keep the reaction as is, you keep the delta H as is, 198.9. Is there any other reactant or product that shows up in only one of the reactions, step reactions? There's an O. There's an O right there. Okay. See, this O3 and O2 for reaction B is not anywhere in the target. So let me take care of all the ones that are in the target, and there's O. So I'm going to work on B and get B prime. But the problem is that my target, the O is on the left, and it's a coefficient of 1. So the first thing I'll do is I'll reverse this reaction. So this is the manipulations that I was talking about. So when you reverse, the rule is, if you reverse the reaction, you take opposite sign of delta H. So the result is now positive. Oh, so what's delta H of the reaction? See, I messed up there, right? This is reaction C that we're manipulating. Let me zoom out so we can see, hopefully see at all of it. Yes, this is reaction C, and we're changing it to a C prime. So I took this reaction, I reversed it. When you reverse the reaction and take the opposite sign, there's your delta H, but when you reverse, take the opposite sign, negative 495. But we're not quite done yet because, see, in the target, there's a coefficient of 1. So now here is a coefficient of 2, so we're going to divide by 2. So we're going to change it to this. And so when you, what did we do? We divide coefficients by 2. Do the same for the delta H. Divide delta H by 2. But which delta H? Not this one. We're working off of now this reaction that we after the reversal, and we divide it by 2. So you could almost do something like this. Divide by 2. You're going to divide that by 2. Negative 495 divided by 2. This is our result, 247.5. Okay. And now O is done. Coefficient of 1 on the left, coefficient of 1 on the left. Okay, but what do we notice? We notice that we have an O3 on the left, but there's no O3 in the final target reaction. We're going to take B and manipulate that. And we are going to reverse it so that O3 is on the right. And see, this O3 here is on the left. So we're going to reverse reaction B to make it 3 halves. O2 goes to O3. Now, right now, I'm not 100% sure if I add these reactions, if I get the target. But let me just finish this. Reverse. Take opposite sign. And it's negative 142.3. The opposite sign is positive 142.3. Now, be very careful. What reactions are we adding? I'm gonna try to add them now because I have taken a look at every single reactant and product in the target, and I feel like I have those set properly in the individual steps. But because of this manipulation here, I got to remember that I'm using this equation, okay, and this delta H. That is my C prime. And I'm using this equation. A was taken as is, and there's my delta H. And I'm using this equation, and there's my delta H. So there are a couple of ways you could add the equations. You could literally write out everything on the left side of the arrow. NO plus O3. We're not using this equation. We're using this one. Plus O plus 3 halves O2 goes to NO2 plus O2 plus 1 half O2 plus O3. Now, I'm pretty confident about the NOs. Okay, I'm pretty confident about the NO. I'm pretty confident about the O. I'm pretty confident about the NO2 because it shows up here. It's this other stuff, the O3 and the O2, that's not in the target. I'm not 100% sure, but you got to take a leap of faith. And if you feel like you've taken care of all of the products and reactants and got the correct coefficients, cross your fingers and hope that these other compounds cancel out. Well, take a look at this. O3 is on both sides. 3/2 O2 is the same as 1 O2 plus a half O2. This is 1.5. This is 1.5 also. Those cancel out. Do you see how I'm left with NO plus O gives me NO2. Oh, and that's our target right there. So if your reactions, individual reactions, add up to the target reaction, then all you have to do is add up your delta H's. So literally we're doing an addition. Okay. Now, do you see why it's a little bit tricky? You can't include this number because this reaction was not the one that was used. This reaction was used after we had divided this by 2. Okay, negative 198.9 minus 247.5 plus 142.3 equals, okay, delta H of the target reaction equals negative 304.1. Make sure for the greater that you put the right units and the right sign and circle your answer. Okay. If I could get this all on one page, I probably can't, or all on the screen. There is a Hess law problem. Okay. I did have 2 problems set up for us to do together. Time is, we're past 20 minutes. Why don't I wasn't planning on doing this, but why don't I take care of these 2 problems in a separate video? Okay, I'll do them in front of you. Okay. But if you want, you could copy these now. I will immediately see you in the next video.